Mostly if it goes beyond this one, then we go with plate girder, because mills cannot produce very deeper W section and all. So we need to go with plate girder only. Plate girders may be used for long floor spans buildings. In our case, we are using all primary girders. Like in, if you see our deck outside, we have leg to leg distance of almost 20 meter and all we have. So this much span we need to provide the plate girder only. It's possible because whatever the plate girder we are used here, if you see these plate girders, it's almost 1500 mm deep. So this much big deep, we don't have any ready-made like a rolled W6 and all, we don't have it. So if you see this plate girder, then we need to size like what could be the this width of the flange and thickness of flange and this thickness of web and depth of plate girder like that. We need to size it. So that's the thing we are going to look at it. If you see like to ensure maximum economy, plate girders relatively deep with a span to depth ratio of 1 in 10 to 1 in 12. That means like if you have a span of 10 meter, then maximum you can go even
1
like
meter.
10 by 12. Yeah, 1 meter also or 800 also it's okay. So 1000 divided by 12, how much it will come? 10,000 divided by 12. 10 meter means it's coming around 10,000 divided by 12 is 830. So you can go with 850 deep girder or even 1 by 10 also we can go. That means like a 1 meter deep girder.
Mhm.
But it has to satisfy both the stress as well as stability and deflection criteria also. Okay, that's why we need to. This is preliminary sizing only. Then we will do the analysis. Then we will come out with the required size. Okay, and
We
this
use the plate grade in the barge, right? When we
plate
are
girder.
yeah, plate grader in the barge for transportation
Yeah,
when
yeah,
we
yes,
are
yes. Yeah,
the
we
put the
yes, yes,
location.
correct.
Yeah,
Because where we have the very big load like U-frame location, we have the jacket transportation time or deck transportation time. This heavy load is coming. So here we need to have something a deeper beam. That only it can carry the loads, right? That's why we
yeah.
have used bigger, deeper girder for transportation location, barge, grillage, and loaded grillage and all. We are using a plate girder. And then this not only increases the flexural capacity but also increases the amount of inertia, thus reducing the deflection. Yeah, it means that whenever we increase the depth of this girder, what will happen means moment of inertia I,
Yeah.
it will increase. If I is increasing, for example, if you have say cantilever PLQ by 3 EI, that's the deflection, right? So if amount of inertia increases, your deflection value will come down, right?
Mm.
If I is increasing, your deflection value will come down. So that's what they are saying, that if this increases not only the flexural capacity but also it reduces the deflection by increasing the amount of inertia. And the web plate may also be fabricated from the steel with the strength lower than the used for flanges. What does it say? That the flange maybe we can use higher grade material like 355. Web we can go with S275 also we can go with. In that case, like what would happen? Because of this web low strength, sometimes we increasing the uh, length, then it will become like a thicker web. It will increase the tear capacity by reducing the slenderness ratio. Web slenderness ratio means if you see the web slenderness ratio, it is ratio of height divided by thickness of web. This height is between these flanges and excluding that fillet, like it will come like this. This is the height. So H by TW will be the flange slenderness, and web slenderness, web slenderness, for flange slenderness it will be B by thickness of flange. That means how much it is extending. This slenderness. If it is more extending like this in the plate girder, it will buckle before the beam bends. So local buckling and all it can happen. Web also, if it is quite deep and very thin web means it will buckle,
Yeah.
right?
Because too thin.
So
Yeah.
Yeah, these are the limit states we need to
Hmm.
understand, like web buckling, flange buckling, web yielding, flange yielding, like that. So many. Uh, we have the limit states. Those things we will see it in this basic chapter only. So it will be helpful when we are doing it in the software also. And especially when we have the primary beams, we are using the plate girder only. So for that purpose, it's better to have some little bit background on this plate girders. Okay.
For the range for the flange and for the web
Yeah.
thickness,
Yeah.
there
Yeah.
is a book or a standard
Yeah. I would tell you
AC.
now in this
Yeah,
presentation, I can
red
tell
book,
you.
right?
Yes, because
Yeah,
that defines the slenderness. Mainly, it comes with the, for example, now you understand like what should be the depth. Depth is coming from the span of the
yeah.
girder.
Hmm.
Okay. Then once we know the depth, that means such value, then we can understand the width also how much it come, and thickness of web how much it should come, height of web how much it should come, flange width how much it's come. Those things and all we can. Now I will tell you in this coming 1 or 2 slides. Okay,
Hmm.
you will understand the relation between these two. Mainly, how these relations are working means it defines the slenderness. From slenderness, we are getting the flange critical stresses, web critical stresses. So stress and the slenderness, these two are related, and this dimensions also related. So we will come to know.
Hmm.
Okay, and then this plate girder has higher fabrication cost than roll section because we are using this weld and all. If you see here, we are putting this fillet weld, so they have to weld all these three plates together, right? So it increases a little bit cost, but it has still further it has some advantages. If you see here, girder is designed specifically for record purpose, because if we need it like for a longer span, we can go with the girder. So it is specifically designed for some particular spans, and girder has high strength to weight ratio. This I will explain to you here. You see in the roll section, it has W36 by 800. It has weight is 800 pounds. Okay, and it's flexural resistance 1000 to 15,200. Moment of inertia 64,000. But if the same thing, if we go with the 65-inch deep girder, almost a similar depth, and with 25 by 2.5, its flexural resistance, if you see, it's almost a little bit increasing. And moment of inertia, you see, almost double the
Double,
times.
yeah.
And weight, you see, almost half of that, roughly half of that. It's 800, it's 470. Yeah, it's
Hmm.
almost 60% kind of thing. It comes right. 40% weight reduction is there. So we can reduce the weight by going with the plate girder instead of going with this kind of roll section if it is a deeper beam is required for that particular load condition and span. Okay, and deflection also it will reduce, because if you are increasing the depth and moment of inertia is quite high, then it will reduce drastically the deflection also. So it's
Hmm.
better for us. Then the moment demand for the girder also reduces. Flange plates may be correspondingly reduced. If you see, if you have the plate girder from one particular span, the bending on diagram will be like this. So we have the maximum moment at these locations. So at these locations we can have a very thicker flange plate, because it will increase this moment of inertia. At this location, this from here to here, its moment of inertia is less. So we can reduce this flange thickness, so we can have some more economy. We can
Hmm.
reduce the cost also. That's what it says here. As the moment demand on the girder reduces, the flange plates may be correspondingly reduced in size. So based on this moment variation, we can have the different plate girder in this corresponding section. That I will show you. Even if you see here at these locations, I have kept it a little bit bigger and wider and
Yeah.
quite deep, like a plate girders. But at this location, it's lesser tickets used, because if you see, this is nothing but it's a kind of we have the minimum, it would come like this. So fixed and minimums are quite high, so we have gone ahead with like a little bit heavier PGs at this location. Especially at these locations, its moment is coming less, and at the middle it will come more. So middle it will become more, but still whatever the section we have given, it's more than sufficient enough. So
Hmm.
like this we can vary this trade girder property so that we can get optimized weight and economy, right? That's what it says here. Let's go here. This is one sample trade girder what we are using it for one of our index, and the span is almost 20 meters. So 20 divided by, well, how much it's
12.
coming?
One
Yeah,
point.
20 divided by 12, it's almost 1.66.
Yeah.
So we have gone ahead with 1.5. So we are going with the 10 to 12 in that ratio, means we can go with even 10 also, right?
Hmm.
Not 10, even little bit more. We have gone like a 13, something like that we have gone. But it's quite enough for us. So we have gone like this, but we can go with even 1600 also. It doesn't matter. That in that case, these flange thickness plates we can reduce a little bit. Instead of 30, it can come maybe 25 like that. Okay.
Mhm.
Then next, it's see like some alternative forms of plate girders are shown in figure 12.2. This one here, see like this is a wider flange at top, bottom is a little bit not wider. Here this is not wider, but this is wider. Bottom flange is wider than the top flange, and here it's almost equal with the double web plate girder. Some cases we could have this kind of situations where we need to go with the double plate girder, because it will increase this. It's wide enough, right? It's wide enough and sort of thick. It has the moment of inertia, much bigger moment of inertia as compared to these two plate girders. And web also we have increased it because it's the shear capacity also it can be quite high, because web it takes the shear. Most of the shear goes through web only, and most of the moment it goes through the flanges only, flange only taking the moments. Okay, these are the examples. Then let's go to here girder proportions. This is what you are looking for, right? Girder proportions. Let's see here. Design aids are available in some book like that provide available flexural and CS and wide range of plate girders. I think they might have given like the plate size, plate girder size, and what's the capacity like that.
Mhm.
That we will see. And if you see here, girder depth, as we have said, like we can
Yeah.
go with LB10 or LB12 in that range, LB10 to LB12, where L is the span. Yeah, deeper girder is preferred for heavier loads and smaller deflections, and shallow girder is preferred for lighter roads. Yeah, so if the load is light, we can go with the shallower girder. If the girder load is quite high and we need a smaller deflection, sometimes what would happen, like we have the plate girder and we have some machinery, some equipments kind of thing like GIS or some transformer, then the vendor would say that from one point to another point, the supporting points where we have the transformer supports, from one support to another support, I need a deflection of L by 1000, like a very stringent limitation, or L by 500. Like that, they could give the deflection limits, because the relative displacement for this transformer is not happen to cause additional load to this one. So they will ask us to limit. In such a situations, we need to go with still further deeper girder, because here deflection governs the size as well as the plate girder, right? So function of this transformer should not be, example I'm telling transformer, some equipment, whatever maybe the equipment, it's not be get impaired by because of the deflections. So to limit the deflection, we go with a little bit heavier plate girder as compared to lighter loads. And once we know the span, we can get approximate depth. Then flange area, the required flange area is appropriately, it's like whatever the moment we need. And then this yield value, height, this is the height, depth of the girder. So area of flange, once we come to know based on this design parameter like 1.67 in the whatever the moment from the our analysis, and height we know, from that we can come to know area of flange. Once we know the area of flange, and then we can come up with the uh, flange width as well as thickness. Even there is some guideline. If you if you know the height, just now we come to know the height, right? Like L by 10 or L
Mhm.
by 12. From the height, we can come to know flange width BF. That should be almost H3 to H5. Means like our gutter is 1 meter deep, means the width can go 1000 divided by 3. How much? It's 300, right? 1000 divided by 3, it's 300. 1000 divided by 5 is 200. So
200.
we can, yeah, we can go with 300 or 200 to 300 in that range. 250 also we can go. And where H is the clear depth. Clear depth means excluding this flanges, huh? Flange thickness excluding that. Okay. Right. Then once we know the flange width, then we know we can calculate the flange thickness, because to provide compact compression flange slenderness parameter, I told you like the this is the flange slenderness means what is this width and what is this thickness. Based on
Mhm.
these two terms, we can come up with the calculation of the slenderness parameter. Once we know this compact flange, compression flange, the slenderness parameter we are limiting to 9.2 for 50 KIC. 50 KIC means whatever we are using it 350 steel. So 9.2 means like B by 2 times thickness of flange equal 9.2. So once we know our width is, I say 300. So 300 divided by 2 into 9.2. that would be the thickness of the flange. How much it comes like 300 divided by 2 times 9.2. It becomes like a 16 mm. So we can go 20 mm also. Thickness of flange is 20 also we can go. It will be 20 or 25 also we can go. That's not a problem because we are still within the compact compression flange. If it is compact compression flange, it would be yielding limit state would come. If it is non-compact, it will go to the inelastic buckling. Then if it's slender, then it will go to the elastic buckling. So those are the limits for this flange thickness. So what in brief we can say that once we know the depth flange and based on this compactness slenderness parameters, we can come to know the thickness of the flange minimum required. And provided this limit is not exceeded, the lateral bracing is adequate. The critical compressive stress equals to Fy. Yeah, there is one more point also, lateral bracing. This is important because whenever we design the plate girder, there is one limit state called lateral torsional buckling. You might have known, right? Like lateral torsional buckling means it will be if you have a cantilever beam like this, it would buckle like this. You might have seen this lateral torsional buckling. I will tell you lateral torsional buckling how
Mhm.
it comes. Okay, 1 minute, just a minute.
Okay.
Yeah, hello, Karim. Yeah, it's Karim. Yeah, I'm going to replay it in a couple of hours. Yeah, a couple of minutes. I'm have one meeting after that. Okay, thank you. Thank you. Thank you. So here we have this. So you understand, right? Here we have the lateral bracing that also we will see it in the next slides. So once we know the flange thickness, web thickness also we can come down. Limitations are placed on the slenderness of web in order to prevent the vertical buckling of compression flange. If you see this uh, girder top portion, it would take the compression. As shown here somewhere, if you see, where is, yeah, if you see here, when the load is coming, the beam would deflect like this, right? So top flange will take the compression, right? Hello.
Yeah, yeah.
Yeah. So if you see the cross section, this is the top flange and web and bottom flange. So top flange, some this will and some portion of the web. This area it will take the compression, right? If you see this bending stress also, this will be the compression portion. This will be the tension
Tension.
portion. So top flange will take the compression. So compression, when it comes this flange, if it is very wide, then it will start buckle, local buckling. It can happen. That's why they are telling here. Limitations are placed on the slenderness of the web in order to prevent the vertical buckling of compression flange. And intermediate transverse stiffness may be required on the one side or both sides of the web to increase the shear capacity of the web. Because if web is too deep, we need to provide sometimes a stiffener. Otherwise, it will start buckling it. Additional shear strength may also be obtained by designing the post-buckling behavior. This we will see like tension field action included on the web or excluded on the web. There are different conditions. You will see this one. An estimate of the required web thickness may be obtained by using American AAC. Mainly it's AAC tables 3.6, 3.7. It gives like what could be the value of height of the web and thickness of the web. That we can get it. And stiffener also, based on the stiffener also, if you see in this one, this is the stiffener distance. We would say this is the panel. So if the stiffness spacing is increasing, it will have some impact on this vertical shear capacity. If it's reducing, it will improve the shear capacity of the web. So stiffness spacing also it matters. Okay. So this A by H and H by DW, this ratio also we need to consider when we are estimating the available shear strength for these webs also. And provided with the with and without tension field action. This I will tell you like with and without tension field action means if you see here it's like a truss it would come top card bottom card and these are the vertical members and this web at this location it would start experiencing the tension here also if you see it would be start experiencing tension and all like this it's like it's looking like a truss arrangement. That's what they're telling like here no tension field action but here tension field action is there diagonal tension field. because this plate it would start experiencing tension in this all this portion of this. If you do some point element analysis, we can say that when we are loading like this, then it will show this is the impacted by the tensor force like that. It is subject to the tensor force. And intermediate transverse stiffness, that is this one, intermediate transverse stiffness you see here. And end we have the bearing stiffness because it is support is there, so that's a bearing stiffness. Intermediate stiffness also there, just to take into account this web stiffness. In accordance with the ASC, intermediate stiffness need not be provided when the required shear strength does not exceed the available shear capacity of the web or web to thickness ratios does not exceed. What does they say? Like if we have the H by TW for 50 KSA 59, if you are limiting to 59, if our web and thickness, this is the H, right? I told this is the H and this is the thickness. In our case, we have the H as 1500. So 1500 will be 59. If I put 1500 minus flange thickness is 30, so 2 times 30 it goes from 60, like 1440 divided by 59. If I put that one 24.5, it's coming. So my web thickness TW is 25.5 or 24.4. So if I provide 25 web thickness, then no need to provide any stiffener. That's what it says. So
Mhm.
from here we can come to know what is the thickness of web required. So H by TW we can limit to 59 for 50 KSA. So we can avoid providing any stiffener also, and this will be compact also. That also you will see. As specified in AIC 360, web to thickness ratio of unstiffened web. If you are not providing any stiffening unstiffened web, to prevent the web buckling of compression flange, uh, that may not exceed the HPTW 260 limit is coming. Anyway, HPT TW ratio we are keeping 59 only, so it will not have any vertical buckling. In addition, the ratio of the web area to compression flange may not exceed 10. Okay, this is also one criteria. Web area to the compression flange area. If you see here, this portion it will be web. 1 minute, I will take this in different color. As I told you, this portion that would experience, yeah, this portion it will experience compression, right? That's what we have told you. The top, this top flange it would experience compression. So what does it say that when we have the top flange compression, some portion, almost this portion will experience compression. So this area divided by this web area. Web area is nothing but from here to here. This is full web area. And this portion is experiencing the compression. That's what it says here. That should be the ratio of 10 it should come. That should not exceed 10. You see here.
Mhm.
In addition, the ratio of web area to compression flange area. Web area is nothing but H into TW. That's the web area. And compression flange area means like this is the BF into TC. This compression flange. These two, if we divide it, it should not exceed 10. That's it. And when intermediate stiffness are provided, the web to thickness ratio is governed by panel aspect ratio. We have seen that panel, right? Like A value also we have seen. That's A by H ratio is there, right? That should not exceed 1.5. If it exceeds, when 1.5, if it exceeds the web to thickness ratio also, we need to limit 232. They are asking us to limit. So if we limit this one, then it's okay. Like intermediate stiffness or provided means like buckling we can avoid. And A by H ratio is less than or equal to 1.5 means we can still this 289. Depth to web to thickness ratio is limited to 289. That means like we can go still deeper H because it's a 289. If it is like exceeds this value, what does they say? Like if we have the stiffener spacing and H, the height and the A, this value, the ratio they are giving 1.5. Suppose my girder is 1.5 depth means if I keep my A as 1.5, it is less than 1.5, right? Suppose if I keep my A as 2, so 2 divided by 1.5 is how much? 1.5 is still 1.33. Suppose if I go with the 3 divided by 1.5 is 2. That means it's exceeding this ratio. I cannot go very deep, right? Because it's a 289, it comes if it is less than 1.5. If it is more than 1.5, we can go only with 232 only. If it goes beyond this one, then web buckling can happen. You understand, right?
Yeah.
Okay. To utilize the post-buckling behavior of web, the panel aspect ratio is limited by AIC commentaries that like AH by 3, A by H 3 also we can go. This is like a post-buckling behavior also if you want to utilize. Post-buckling strength means the panels in the web plate girder are bounded by top and bottom by flanges only, and either side of the transverse stiffness also there. And low shear loads are resisted by the development of the uniform shear stress in the web of the girder. See, when we see the shear stress, it would come like this. But most of the shear is taken by the web, this portion. That's what they're telling here.
Mhm.
Low shear loads are registered with the development of the uniform shear stress in the web of the girder at onset of web buckling. At the onset of the web buckling starts means a panel with the stiffened transverse stiffness does not collapse, but does exhibit slight lateral web displacement that are not of structural significance. However, the panel can continue to support the substantial increase in the load in the post buckling range due to the development of the tension field mechanism. What does it say? Like when we are putting some load, if this location little bit, this it can buckle. That's what they are saying, right? It will not collapse, but it is slightly it will show some lateral web displacement
Mhm.
that are not structural significance, but once it little bit laterally displaces, say for example it displaces like this, see little bit lateral displacement, still it is taking more load, it will start taking the load. That is the post buckling they are telling. That's the mechanism, only tension field mechanism they're telling. So it will start taking this as a diagonal tension field. Okay. The shear load is now carried by the diagonal tension membrane stress in the web. So here in this case, the shear load, even this diagonal also it start taking. Okay. And transverse stiffness acting as a strut by the top and bottom flanges acting as a chords, thus forming an effective Prater interest. What does they say means? Like this vertical stiffener is there, right? It acts like a load taking member. This also load taking member. If you see this, this would act like a truss member. This is the tension field one. This is the vertical member. This is another tension field taking member. This vertical stiffener. Like it forms like a truss, truss or end truss. In the post buckling range, the resistance offered by the web plates is equivalent to that of the diagonal ties and bar in truss. Yeah, this is what they are telling. Like it acts like a truss member. Web panels on either side of the intermediate stiffener provide an anchorage for the diagonal tension field. No such anchorage is available on the web panel containing a large hole. Okay, sometimes we will be having some some opening also. That and all, we are not using it in our structural props or and all. No such anchorage is available because once they put the stiffener, that will provide some anchorage for this diagonal tension field. Hence, in this panel and adjustment panels, designing using tensile field action is not permitted, and shear capacity is determined from AIC 316. What does it they say means? Like whenever we have some openings in the web, this kind of tension field action we cannot utilize. It's not permitted, so we cannot use that. Take the advantage of this tension field action and all. And in the case there is a panel on one side only, and anchorage is not available for the diagonal tension field. Hence, design using tensile field action is not permitted in the end panels. And large panel aspect ratios, tensile field access inhibited, and the design using tensile field access not permitted. When exceeds A by H exceeds 3. Yeah. See, that means like if we have some plate girder and we put some spacing of the stiffener is too high, and this is the spacing distance between the stiffener, and this is height. So height is 1 meter, A equal to 3 meter means that time what would happen? This tension field action, it will not develop. So we cannot take the advantage of that. If it is very close stiffness, we can take the advantage of that. If it exceeds A by H ratio more than 3, then we cannot use that tensile field action. That's what its AIC is talking about. Tensor field action is not permitted in accordance, especially when A by H ratio exceeds 3, we can't use that one. And also this one, like you see A 2AW by AFC by AFT, if it is greater than 2.5, tensor field action, we cannot use it. This condition they are giving it. This is compression flange, this is tension flange, this is the area of web. Area of web, area of flange tension field, tension flange, area of compression flange. So we need to compare that area of compression flange, tension flange. So it's web also. So we need to see these values, okay? And H by BC, if it is greater than 6, we cannot go. H by BT also, if it is greater than 6, we cannot use these values. We cannot use this tension field action. Okay. So there are three possible approaches for the shear design of plate girders. One is unstiffened web, another one is transverse stiffener without utilizing tension field action, another one is transverse stiffness with tension field action utilized. That we will see it now, like design for shear with unstiffened web means like just now I told, right, the H by TW, that is the slenderness parameter. Based on this slenderness parameter, the failure can happen in web either by plastic yielding or inelastic buckling or elastic buckling. Plastic yielding means that's for compact web. Inelastic buckling means non-compact web, and elastic buckling means slender web. So you might have a question like, how do I say that whether the web is compact or non-compact? That's by by limiting this one. Like you have the H by TW value. Say if it's like a 50, and if you if you have substitute all these parameters 1.1 into kV E is young smallest, kV is a shear coefficient, that is by shear buckling coefficient, that is 5. If you substitute all these things, it will come around some 54 something. So your H by TW ratio is less than this, then it's classified as a compact web. If it is compact web, it will have only the plastic yielding as the limit state parameter. If non-compact web means between these two ratio it will come. Based everything is depends on this slenderness ratio. That slenderness
Mhm.
ratio depends on H by TW. So based on these values, we can define whether it is a slender web, non-compact web, or compact web. Once we know this compactness, then we can define. Then we have the corresponding formulation for checking the shear capacity. If you see here, to produce the elastic buckling, the web minimum slenderness parameter is 1.37 value. That is this value. That becomes slender web. If it is 74, if it is less than 74, it's not slender web. It is non-compact. If it is more than 74, then it becomes slender web. Plate girders may be expected to exceed these limiters, and hence nominal shear load is given by 0.6 Fy Aw and Cv, this coefficient. Okay, and this coefficient is nothing but like 7.5 E by Fy H by T squared, it will come. And on example, you will see this unstiffened web, there is no stiffening. Determine the available shear capacity of the welded plate girder for grade 50 steel they are telling. So here you see the area of web is nothing but d into t, that is 75 is the total depth, and the 0.35 is the thickness of this web flange. Sorry, web 0.375, 3 by 8, right? So this is the web area. The unstiff web is unstiffened, and the web plate buckling coefficient is kV is 5. If it is unstiffened web, then web plate buckling coefficient is 5. So once we know HPTW ratio, it's 192 comes, it is less than 260. That means no need to provide any stiffness. And if you see HPTW value, if you calculate, it becomes uh, this value, this 1.374 is there, right? That's elastic buckling, right? So the equal 74. Our HPTW is 192. So our HPTW is crosses the 74. That means elastic buckling web governs. So we need to go with this equation. Then 0.6 Fy we know, AW also we know, the CV we know, like from this value it's 7.5, all these parameters. So if we substitute this 7.5 E by Fy into HPT per dW whole squared, it becomes 100 kips. Then if we are going with LRFT, that's a shear, design shear, 0.9 factor, we will be putting the factor here. Allowable shear capacity, normally we go with AST only. Allowable shear capacities with this safety factor also, we need to divide this nominal shear. This is nominal shear. What we are calculating, allowable shear. Allowable shear to nominal shear is factor of safety, we need to divide. Then we will get 60 kips. This is the allowable shear capacity of this web, unstiffened web. Okay. And we will go with the next one. Design for shear with the stiffened web. What we have seen is unstiffened. Now it's with the stiffened, and tension field action also excluding. We are not considering the tension field. We are excluding it. The nominal shear capacity of the plate girder with the stiffened web depends on the plate, that web, same web depth to thickness ratio TW, and panel aspect ratio also, because we are stiffening it. So it has two parameters, H by TW parameter, another parameter is A by H, the panel aspect ratio. This is nothing but panel aspect ratio. The shear buckling coefficient KV. So these three parameters, it depends on defines the nominal shear capacity. So someone can ask you what are the three parameters that defines the stiffened web shear capacity. HPTW, that's the slenderness. Another one is A by H is the panel ratio. Another one is KV, that's the shear buckling coefficient. The shear buckling coefficient for stiffened web is 5 plus 5 divided by A H squared. All these parameters we know. And nominal shear strength for the girder transverse stiffeners, same thing, 0.6 into Fy into Aw into Cv. This shear yielding of web happens like HPDW is within this limit, means it can happen shear yielding. If the inelastic buckling also can happen if this is within this limit H by TW. This web slenderness, if it is within this limit, then inelastic buckling can happen. That time CV value is this one. And elastic buckling means if H by DW it's exceeding like 1.37 kV, that we have seen right here, 1.37 kV. If it is more than 74, then that elastic buckling can happen. If it is elastic buckling with the stiffened web, we have this parameter 1.51 into E into kV. This formula we need to put it. If you see one sample also here, stiffened web with tension field action excluded, same problem only, the same like 75 by 0.37 face our total web area. Panel aspect ratio is A by H. They have the stiffness spacing they are given, right? Stiffness spacing 80 inch. So 80 divided by 7 and 72 is 1.11 only. So when we know A by H is in this ratio, then KV values we will get 9.06. Web to thickness ratio it's 192. That's greater than 99. So elastic buckling can happen. Hence the shear buckling coefficient is given by, if you see here, this is in this condition, elastic buckling. So CV value we need to calculate based on this one. Suppose if it is an elastic one, then we might have gone with this. Or if it is only the shear compact web, then we might have gone with CVS one. It is not it is not a compact one. This is like a slender one. That's why we are going with the CV value 1.51. Once we know the CV value, we know from 0.6 FYAW, this CV, that's additional shear buckling coefficient, we need to multiply. It's just from 0.22 only. So it will have allowable load, it will be like only uh, here we need to see it 185, right? 185 divided by 1.6, 111 only keeps it comes. But if you see AIC table with this H by DW and A by H ratio, it automatically gives this is the allowable load like that. That's from the manual. Here this one from the calculation. Both are almost equally matching. You understand, right? Or when we have the stiffened web, we are having this CV coefficient also, right?
Mhm.
Unstiffened also we have the CV coefficient, but CV coefficient is we are taking with almost one only, because if it is compact web, we will take one. If it is non-compact web, then we will have the CV value also. We have to calculate it. That's based on this formula.
Okay.
And the same way, if you go to shear, design for shear with the stiffened tension field action included, exactly same thing it would come. Here also we need to see three parameter it will be including. The shear buckling coefficient, KV value will be same thing, that CV value is the right, that it varies. That's elastic buckling shear coefficient. It varies with respect to the slenderness of the web as well as aspect ratio also. Here, if you see nominal shear load, it is taking 0.6 F by AW. If it is shear yielding, elastic buckling, it will have CV value. Here, CV value is almost equal to 1. So this is also one example. I will send you this. You can see, like once we come to know the area of web and the A by H panel ratio, we know this KV already we calculated it. HPDW is 192. It becomes like a elastic buckling. And then CV value 0.2 it will come. With this girder with HPDW in this value, nominal shear strength is given by 0.6 FAW CV 1 minus CV, this value we need to put it, then we can get this 569. 569 means 341. See, you can see the three values, same problem only. One is unstiffened, we are getting how much? Only 60 kips. With the stiffened one, the same depth, same everything, stiffened web, we are getting 111 kips.
Mhm.
With tension action included, we are getting 341
500.
kips. 341 kips after taking the factor safety.
Mhm.
So 64, 60, then 111, that becomes almost 341. So with stiffener and with tension field, we are getting much bigger capacity because we are keeping the same HPDW. We are not increasing the web height or web thickness. We are not changing anything. So with this 192 only, when we have the stiffener, it is increasing the web capacity. Okay, web shear capacity. And design of transfer stiffeners. This I will tell you, like tension field action excluded. The stiffeners must be adequate rigidity perpendicular to the plane of the web, driven lateral flexion throughout their height for loads up to the shear buckling load. That means like we have the web, right? We need to keep this stiffener. It should be able to prevent the lateral deflection throughout their length height for loads up to shear buckling load. Intermediate stiffness may consist of pair of stiffness provided on opposite side. Like usually we would be having pair of stiffness on opposite sides, or single stiffener on one side of the web. That sometimes it happens. The required moment of inertia of single stiffener about the face in contact with the web plate of a pair of stiffener is provided. What they are telling the how to size the stiffener, because we are told we are providing the stiffener. So okay, you provide the stiffener, but what will be the thickness and width? That we are calculating from here. This transfer stiffener factor also we need to calculate. That depends on this, once again, the panel ratio, and B equal to smaller dimension of A by H. That's okay. That value is like between the A panel stiffener to stiffener distance or height of the panel. Since the tension flange is self-aligning, the stiffness can be stopped short of the tension flange. This avoids potential fatigue induced cracking occurring if the stiffener is welded to tension flange. It's nothing but if you see here, yeah, this one, this is the tension, bottom is tension, right? Here it is stopped here, it doesn't go here because it's a self-aligning flange tension. That means what they're telling that even we can stop it here like this, no need to always take it down. But if you see the bearing stiffener, we need to bring it down because load is coming here. Okay, that's what it says here. That's okay. And stiffener may be stopped sort of tension flange with the welding terminated distance from the near toe. Web to flange weld between 4 times thickness to 6 times thickness. When string 4 times thickness to single time thickness, like this, when we are stopping it, almost this web is 5 mm, means we can give a gap of 20 mm. We can stop the stiffener. When single stiffener is used, they must be attached to the compressed flange to resist any twisting flange. Okay, that means only one side we are using single stiffener, we will have to take it full. And if you see transfer stiffener, tension field action excluded. Same example what we have seen earlier. Clear spacing 80 only. A 80, H 72, A B H ratio we know. Thickness of web also 0.375 inch. And from this, the J factor we know just now we have seen. With this input, we can come to know with the moment of inertia of the stiffener. And one small plate, like 1/4 inch plate, we are taking that to give the amount of inertia is 2.25. That is more than this 1.9. And we need to see this limiting width to thickness ratio of stiffener also. When we are providing the stiffener like this, we need to see what is the width and what is this thickness. If it is very small, large width and a very small thickness, if we provide, that will become like a slender one, that will start buckling. Okay, to avoid this one only, we are keeping this kind of limitation. If a width of stiffener to thickness of stiffener, we need to keep it almost 16. So if you have a width almost 160, you need to keep it like at least divided by 16 means 10 mm, right? The same way width to thickness ratio of the stiffener, this is the one what we calculate is 12. It is less than 15.9, so it's okay. And this I will tell you like one more thing also. This is not a problem. How to calculate the stiffener of the transfer stiffener sizing it. I'll show you one sample for this. You see here, I'll model it one plate girder and apply some load. You will understand how much it's coming, right? Hello, Majid,
Yeah, I'm with you.
you with me?
Yeah, I'm with you.
Yeah, yeah. I'll add one small plate girder. You will understand. Let me put like into one. Then I'll add some member. From here, I will take it say around some 20 meter, right? This is what I'm trying to do it. Okay. Hello.
Yeah, I'm with you, Mr. Raj.
Yeah. Okay. Okay. So group label PG1, I will put it, and joint properties, I will keep it here as pinned, and then property of this. So I'll put it at subplate girder PG1. I'll put it maximum depth. I am giving it 1150. Yield is 355.5, and here we can give plate girder width as 300 and thickness as 30 and height as 150 and web thickness as 20. Okay, you got it.
Yeah.
And then I'll put this as we need to keep this in the support with the torsional restraint also, and we will put one load on this member as 0 1 some sample condition. I'm putting concentrated load, and the concentrated load of say I can put something, it will take even 100 200 tons also. I'll put something minus 60 tons, and at the sun distance of 10 at the middle I will put it. So I'm keeping it 60 tons load. Okay, and then what I'm going to do, I'm going to put the analysis options. We will put the code check AAC in that is, and number of segment and all these things. Okay, additional we will ask this input and joint reaction deflections, all these values we will ask for it. Element details, we will ask for all the element details. Non-table check, it's okay. Special, I think is that I guess also this we will update it. So we will keep this model design tubular member. I'll put PG plate girder. Okay, I update here. So if we see here, plate girder, I have defined it, and two joints with one load, and this analysis also code check we are using it AAC 1337, and report view we have asked for all the reports like the joint deflects and all these things, and then we will make on a run of this analysis generator. We will do some static analysis itself, and we have the static analysis. Okay, so if you go to this analysis data, we can see this utilization ratio is very less, 0.09 only, so it can easily take the uh, load. And I have the shear load also. See distance, shear force is only 294, Okay. And shear load 294 kilonewton. This is the shear stress is only 9.81. Okay. That's the web it will take. Here you see the plate girder stiffener report. We did not give any stiffener, right? And we are
No.
given only web height 140, web thickness 20, I mean 2 centimeter. So shear force is 294, shear stress is 10.5. It is calculated. How it is calculating? It is basically the web area it will take. Right, web area, how much it will come? 140 into 2, that is 280. So 290 centimeters squared. So 294 divided by answer, if I say 10.5, it would come. So this is the force divided by this is the area. If you multiply these two, you will get the shear stress. Okay. CV required, web stiffener 0.83, required space none, gross area none. This is nothing but web stiffener, but we have not given any web stiffener. This is unstiffened plate girder, right? Unstiffened plate girder. It is calculating CVS 0.83. So if you see it here, unstiffened plate girder, unstiffened plate girder CV value, right? So if you see here, what is my CV value? 1.51 kVE FY, and that means 7.55 into E into FY into H by TW, right?
Mm.
So if you substitute value 7.5 into E is what? And here we have the Young's modulus, all these values we have it here. Here you see Young's modulus and all it will be coming. Slenderness, billet well depth, the CE value 20 into 1000, right? 20,000. So E value 20,000, FO is here 355,
35.
and H is what? H we have seen 140, right? Here, height we have seen, right? Is the height. Just now we have seen it. Yeah, here. Height 140 and web thickness 2. So we will put it height is 140, web
70.
thickness. Uh,
Yeah, it will be 70 square.
web is 20, right?
Mm.
1400. In mm we will put it everything.
Mhm.
Whole squared. In DFI is 355. Right. So this value, this is all this 7.55 E, right? So 7.55 into 200,000 it will come, right?
Yeah,
So
this
what's
is the
the value
value.
it's coming? 7.55 into 200,000 divided by 355 into 1400 divided by 20 square. 0.868 it's coming. So what's the value it's giving here? 0.83. Yeah, approximately it's coming. So this is how it calculates, huh? Okay. And then bearing stiffener concentrated load is there. Stiffener required, it says yes. Then we can put the stiffener also
Mhm.
where we have the we have seen here, right? The model we have seen where we put the concentrated load of 60 tons. Here we put the load, right? Concentrated load. Yeah, here this location we can put the stiffener. That's what it's saying. Concentrated stiffener required, yes. Okay, no issue. Uh, so once we know this CV value, once we know the CV value, we can substitute CV. AW we know that is nothing but H by TW, and FY also we know. We know the allowable nominal shear, and allowable shear is nothing but that divided by 1.67. So that's how we can calculate for here in this one also. You understand, right?
Mhm.
Yeah, here it will give the allowable shear load, internal load. Here if you see allowable, it will give the allowable shear stress Allowable shear stress is allowable stresses. Upright stress, allowable stress. Also, it will give the shear stress. Also, it will give axial stress, bending stress. This is the actual loads. Upright stress, allowable stress, allowable stress. Here, if it is not giving here, let me check it here from this one also. If you go here, member, review member, see here, allowable shear stress 142. It's coming. So this is the value it is taking also. Okay. So this is what I wanted to tell you.
Mhm.
And flexural design of plate girders. What we have seen is only uh, shear capacity. The same with flexural design, we need to have this allowable bending stress. If you see here, bending stress 26.41, it's coming right. 26.4. This is the allowable bending stress. This also it has some limit states. If you see the web is doubly symmetric, non-hybrid, high grade, so it is classified as slender web. When the web to thickness ratio of web exceeds H by DW. If H by DW ratio exceeds this one means then we are calling this as a slender web. And H is the clear distance between the flange and welded, and TW is the web of this web thickness. And applicable limit state for flexure: compression, flange yielding, lateral torsional buckling, compression flange local buckling, tension flange yielding. So these four limit states are there: compression, flange yielding, lateral torsional buckling, and compression flange local buckling, and tension flange yielding. Okay, these are the four limit states. We need to consider all those four limit states, it should pass. Then flexural design is given by these factors. This is resistance factor. This is the safety factor. If you are going with LRFT, this is the resistance factor. If you are going with AST, this is the safety factor. So if you go to the compression flange yielding, nominal flexural strength of the plate girder when the with the slender web cannot exceed the yield moment. In addition, the lateral buckling of slender web results in loss of compressive capacity in the web, since an increase in the strain does not result in the proportional to increase in the stress. To compensate for this, nominal flexural strength capacity is reduced. So we can say that if you are going with this formula, it accounts for this lateral torsional buckling as well as slenderness of the web also. If it is web is slender, it cannot go with yield moment. Definitely, it cannot reach the yield moment. It will be less than that. That's why we have to go with compact web. Then we can have this. If you see here, this is the one I wanted to tell. If you are within this range, if we are within this LP value, lateral torsional buckling one, we can go until yielding. If we are going until this range between this LP to LR, it is inelastic stability to happen. After, if it is still for the long length, means elastic stability instability would happen. If it is elastic instability, you are bending on to allowable bending on, it will come down. Lesser value it will come. If it is close to this LP value, or bending on will be allowable bending on will be more. That's what it says. Like here from this formula also it will come this value if you calculate. Elastic section modulus we know. Fy also you do know. RPG is nothing but the reduction factor, like bending strength reduction factor. That factor, how we are calculating means based on this lateral buckling as well as the slenderness of the web also. AW is the ratio of web to compression flange area. HTW is the web area we know. AFC is the flange compression flange area. Okay, if we put all these factors here, then we will get this reduction factor. So we can normally what we will say, like a bending stress is the section modulus into yield value, but reduction factor also we need to take into account. So if it is lateral torsional buckling, if you see lateral torsional buckling is influenced by unbraced length. If you have very long beam without any lateral restraint, it can have the lateral torsional buckling. Okay, so this unbraced length it matters, because if unbraced length only influences the lateral torsional buckling. And normal flexural capacity depends on the critical compression stress of the flange, this FCR value. It's not Fy, it is FCR. And the nominal capacity we can see rpg into FCR into Sx. So we have to calculate this FCR. FCR depends on the these values lb by lp. Lb is the length of beam segment between the points of lateral restraint, that is this one. This is the lateral distance between the lateral restraints. And lp is the maximum unbraced length for the limit state of yielding. If yielding need to happen means what could be the maximum length we can keep it for unbraced, that is the lp for yielding of limit state. Then L R also it will come one more. That is the inelastic lateral torsional buckling limit, maximum unbraced length for the limit state of inelastic torsional buckling. So if we see here, if we are within this LP value, we can go with FCR is nothing but Fy yield value. Until that we can go, because it does not happen. Lateral torsional buckling, it will not happen if LP unbraced length is within this LP value. LB is less than this LP. LP is the maximum unbraced length for limit state of yielding. Okay, that we can calculate based on this radius of gyration and E and Fy value. Based on that value, we can calculate the maximum unbraced length for limit state of yielding. So this is the yielding inelastic stability and elastic instability it would happen. And if you go with the inelastic lateral torsional buckling, within this range, suppose we are exceeding this limit state of lateral torsional buckling yielding one, and we are less than this maximum unbraced length for the limit state of inelastic lateral torsional buckling, we can go with this formulation. That time FCR is including this CB value also it comes. CB value is moment bending coefficient. This depends on the maximum moment at different sections. MA means at the 1/4 of the, if I have the beam here, 1/4 of the beam, what is my MA? At middle, what is my moment? At the 3/4, what is the moment? Based on all this value, we can calculate the CB value. One thing I want to tell you, like in our example, this is our example, right? In this example, what is our unbraced length? Means almost 20 meter I have. I don't have any lateral restraint. Okay, 20 meter if I have means I can see what is the lateral torsional buckling, that limit length and all it will give. Here if you see plate girder, web crippling, web stiffener, bearing stiffener, it will give this moment also, LP value and all it will give. Slenderness, shear force, maybe it is not giving it here. I would go here, member, review member. This is buckling already happens, like Van Mises also it comes into picture. Because if here I have very big length of lateral torsional buckling, 20 meter. So we need to see in this one, if we put this value, my 1.1 into RT. RT is the BF. BF is the flange with like 300 mm we have, and divided by uh, 12. This AW is nothing but we have 0, so it becomes 12 only. Square root of 12, right? BF divided by square root of 12. That means 300 divided by square root of 12 is 86, right? This value is 86, it comes. So if I substitute here, 1.1 into RT is 86 into E is 200,000 divided by FY is 355, power 0.5. If I put it becomes like a 2 meter only, 2.2 meter only, but I have given 20 meters. So it becomes like this is not the buckling one. That's why if I see my FCR value here, it is not giving the FCR value, but we can take this FCR value in the output. We can see how much it is giving also. Plate Girder stiffener report, it's giving member detail report. One more detail I will tell you in the another example. See, it will give unbraced length. See, unbraced length 20
Mhm.
and Euler buckling is 20, slender is 35 and 371. So it's like a slender beam it will come. Slenderness ratio and all it is very less. I will tell you one more example also how to calculate this LB value. But it's a simple thing. E value, Fy value, um, flange width, and if this LP value is say 5 meter only, but I have given my PG as 20 meter without any lateral torsional buckling, means this one what would happen? I cannot take this FCR as equal to Fy. Yielding will not happen. It will go to the elastic torsional buckling. That time the value I need to take this one, because CB value pi squared E and LB. LB is our whatever the length complete 20 meter divided by radius of gyration. This value it will come FCR value. It will reduce, further reduce, because I don't have any lateral support, right? So because of that it will come down. That becomes like elastic torsional buckling mode. Okay. I will show one sample, then it will be clear. This is for the flange lateral torsional buckling limit state. Another one is compression flange local buckling. Because if compression flange also, if it is very wide and low thickness, means if it is, sometimes we go with very wide, like 400 mm, 500 mm, 600 mm, even 800 mm also we go. And thickness, if you put it only very less, 10 mm, 20 mm, then it becomes this locally it will buckle. That's the limit state compression flange buckling. That's what it's saying about here. Local buckling of the flange is influenced by flange slenderness ratio. Flange slenderness ratio means this B divided by 2 times B by 2. That means this extent TF by thickness ratio. So if it is compact flange, we can go until yielding. Non-compact means non-compact we cannot go until yielding. And slender web it will become elastic buckling. This non-compact will become inelastic buckling. This all depends on the slenderness parameter. Lambda is PFP to here to TF, and this is the critical stress. You see critical stress also it comes down
Yeah,
whenever we go with a slender. Its critical stress comes down. The same way here also. If my unbraced length is very high, my critical stress is comes down. That means if FCR is coming down, my allowable moment also it will come down.
we'll do now.
Yeah. So lambda, this flange compact, we have to see if it is compact, then local buckling does not occur. Then FCR value is equal to Fy. That is this value. If it is compact, then FCR value equal to Fy. If it is non-compact only, it comes down. This F equation F5 weight, that one only I'm talking about here. Okay. Then if it is slenderness parameter of the plate girder, once we calculate this one for this even the lateral torsional buckling, to avoid any lateral torsional buckling, we need to keep 10.8 and all. If we keep like this parameter, then we can avoid this slenderness parameter to prevent lateral torsional buckling. And lambda p is between these two, means flange is non-compact, then we can calculate the FCR value is this value. This equation is there, right? That we can calculate like this F5 by 8. That is nothing but this one. And F59 is 0.9 times E kc lambda squared. This value is there, right? It is you can see even this curve also is parabolic, because this term is lambda square. Here it is all are linear, that's why it becomes linear. What it says that if you increase the slenderness, you will reduce your allowable stress. That's what it says in simple nut terms. One sample example also it is given here. We will design the flexural capacity. Compression flange area, we can see this is the web thickness. Ratio of compression flange to web thickness, we can see this factor. And moment of inertia section modulus, radius of gyration plus 1/6 of the web BF by this value area of web. This is the ratio of compression to flange area AW. Then web to thickness ratio, it's 192. That means like F5 applies. F5 means like it will be like elastic buckling, it happens. Limit state limiting slenderness parameter of compact flange, if you see it here, this lambda b is this value 9.2, but our value is 6. That means okay, this becomes compact only. So critical stress for local flange buckling FCR Fy. This is nothing but this region, because it becomes compact only, right? Because b by bfc by 2 fc is a 6 value until limiting is 9.2. So it is compact. So compact means FCR value we can take as Fy, and limiting unbraced length we can calculate 1.1 into Ry. This is the what I was telling you, like 4.81 we have to put it here, and E by Fy, then we can get 10.6 feet. So we have the limiting unbraced length 10.6 feet. What is here? They are giving singles over a simple span of 54 feet. That means where is this and where is that? The limiting unbraced length for limit state for inelastic buckling, if you see 36.2, this is inelastic buckling. Until 36.2, it will become inelastic buckling. But here we are having actual unbraced length is 18 feet, because they are telling, I think, with lateral bracing also they are putting at 3 points. So 54 divided by at 3 locations, they are giving the lateral support. So this is total 54-meter length. In that 54-meter length, 1, 2, 3, they have this support. So divided by 3, if you put 18 feet. So if I see here, this is a 10.6 means limiting unbraced for the limit state of yielding. This is for inelastic buckling. So it is between these two. That means it will go inelastic buckling only. So we can take that inelastic buckling factors. This value is coming for the inelastic buckling, right? So we can take this value and we can see this FCR value 45.66. Then the plate girder bending strength reduction factor we can take this value we have seen earlier. So we can go with this FCR we have calculated here. This is the one it governs 45.6 F less than Fy. We should not go with Fy value because it's less than Fy value. Fy is 50, but here we have 45 only from the FCR critical because it's inelastic torsional buckling. So we can calculate this value like this. And design of bearing stiffness, we have seen the bearing stiffener. It is, we have to see the effect. It's like a column we need to consider, like compression element. So once we know the lateral like effective length and radius of gyration and overall height, we can calculate the slenderness ratio. Then with slenderness ratio and area of cross sectional and yield value, if it is less than 25, KL by R is less than 25, we can directly go with yield value. If it is more than 25 slenderness value, then we need to calculate this uh, with thickness ratio. If it is 10.8, then we can go with Fy value. Otherwise, we need to go with this reduction, right? This way we can calculate this. This is not a problem. This I'll tell one more example also sometimes. See here, end reaction and live load it is given. H ratio is there, B by T is the 11.3. So it is less than 4.8. So we can go with this case. So effective column spacing of two stiffener plates stiffener. Yeah, this one also you can see this is the value. Like if it is in between, we can take from here. It's a 12 times T, 12 times T. We can take that much area we can consider for the bearing stiffener. I'll show you here one example. Where is that? Bearing stiffener. Okay, it is not there. This value only I'm talking about. They are calculating this cross sectional area, right? One minute, I will show you. This is our web. Here we are the stiffener and here we are the stiffener. So we can take cross sectional area, this all this cross sectional area for the compression load bearing stiffener. This extent is nothing but 12 times thickness of web. This extends also 12 times thickness of web. That's what here they are taking. And 2 BSD means this is the width of the stiffener